we are going to now explore what it means by work done by a force. Now, let's consider a very simple example. Let's say we have a block over here, and we are going to pull this block with a force F, and we're going to pull it over a distance S. And so by definition, we say that the work done by this force over here is simply force times distance. Now, it is very important to remember that this only works if both the force and the distance are in the same direction. And so let us consider a second example, right? Something similar, but this time, right, we're going to apply the force at an angle like so, okay? And we're still going to travel horizontally like this. Now, keeping in mind that the force and the distance must be in the same direction, then we need to do some resolving over here. And so we have to find the component of the force, which is in the same direction as this distance or displacement that this block is going to travel. And so if we know this angle over here, then this component will be F cosine theta. And we can say that the work done is therefore F cosine theta times the displacement S. And so we have some other interesting scenarios over here, right? This is an interesting one. If the force is applied in a direction that's perpendicular to the displacement, then by that logic, there is no component of the force in the same direction as this displacement, and therefore the work done by this force is 0. There is also another interesting example, okay, and that is, what if the force is applied this way, but your displacement is that way? In which case, right, we can say that the work done is negative F times S. And so you get a negative work done if your force and the distance moved is in the opposite directions. Now, some of us may ask, oh my goodness, how on earth does this happen? Is it even physically possible to pull one way but the object moves in the other way? Well, when it happens, it just means that the force that is doing the negative work is probably not alone. So consider an example that I think some of us can relate to. Let's say you're on a slope. There's a huge mess over here, and you may be trying to stop it from falling down, but you're simply not strong enough. And so you are applying a force in this direction, but the object is moving in the opposite direction. And we all know that that's because probably the component of the weight along this slope is much stronger. Let's call that mg sine theta. And so we can say that U, the force that you apply, this one over here, is doing negative work. But this component of the weight here is doing the positive work. And so overall, the block is still sliding down. There's still some positive work done on the block, and that's why it's gaining kinetic energy as it slides down. But it won't be as much as if you weren't there, because if you weren't there, then this would not be there, and he can probably gain more energy because the net work done on it is higher. Now, in any case, right, this is the idea of the work done by a force. Now, you may be wondering, what if, and this is actually a very relevant question, if you are pushing this block like so with a force F, now it is very unlikely that F will be constant. F is likely to vary over time. And so we must understand the more general way of calculating work done, and that is actually the integral of F ds. And so remember, in physics, whenever we see an integral, we are talking about the area, right, under some graph, and in this case, the area under a force displacement graph. And so typically, right, you may see something like this, force displacement. Okay, your graph may look a little bit like that. Okay, and so the work done is simply the area under this graph.